Hi, my name is Tom George, and welcome to Physics 2212 Lab 4, Circuits. So, the purpose of this lab is to help further our understanding how ohmic resistors and capacitors in circuits operate in both parallel and series, and why real-life resistors may deviate from these results. The model we're going to use is the Virtual Circuit Construction Lab, which is PHYS. And then some fundamental physics principles are the loop rule, junction rule, conservation of charge, conservation of energy, steady-state circuits, and Ohm's law. And our experimental and theoretical results largely match up, and the relationships between resistors, capacitors, current, and voltage in series and parallel are discovered. So some ideas. Ohm's law is this first equation to the right. The voltage is equal to the current times the equivalent resistance. The loop rule states that because of conservation of energy, the sum of all electric potential differences around a loop is zero, which is shown in the second equation. In the junction rule, because of conservation of energy, the current going in at any given point is equal to the current going out. So, lab setup. The initial conditions. For circuit 1, the circuit is in steady state. For circuit 2, the circuit is disconnected prior to the experiment. The system is the circuit and all of its components, and the surroundings are nothing. Some assumptions. The wire, ammeter, and battery all have no internal resistance. We also are assuming that there are no external changes in the magnetic field that are inducing a current in the wire. In general, no external forces. So, first we are given this circuit and asked to predict the current I1 and I2. We calculate those to be 0.02 amperes. Putting that into the simulation shows that it was approximately the same as what we predicted. What does the ammeter read when inserted backwards? Well, the magnitude of the current is the same, but because it's inserted backwards, the sign is now negative. If one of the ammeters is replaced by a voltmeter, how do the readings change? Well, the ammeter now reads 0, because the circuit is now open, meaning charge is not able to flow from one end of the battery to the other. The voltmeter reads the potential difference between the batteries, because when disconnected, the rest of the circuit is basically irrelevant and is just equivalent to the potential difference between the batteries. So as you can see in our graph to the bottom right, it shows that the sum of all potential differences for a round trip across the circuit is 0, basically just affirming the loop rule that we discussed earlier. And then finally, when we attach the voltmeter, we alter the circuit. So why didn't the ammeter reading change? Well, voltmeters have very high resistance, so very little current went through them. This means that the net current through the main wire did not decrease substantially, and so that's why the ammeter reading did not change. So when we replace the voltmeter with an ammeter in parallel with a 100 ohm resistor, what happened to the current through the other ammeter? Why? So this is the situation depicted in the picture to the right. The current through the other ammeter almost triples, going from 0.02 amperes to 0.06 amperes. This is basically because the voltage drop is the same in parallel branches, and because we're assuming that the wire and the ammeter have no resistance, basically all of the current goes through that top branch, meaning that the equivalent resistance of the circuit is about 1/3 of what it was in the prior circuit. And with the same voltage and 1/3 the resistance means 3 times the current, just as we saw. And then so we can now calculate the resistance of each of the following circuit elements. So we figured out that the resistance of the 47 ohm resistor is 48, the resistance of the 100 ohms is 102, and so on and so forth. Basically what we were expecting. So in an RC circuit, which is depicted to the right, the circuit is comprised of the battery, a resistor, and a capacitor. Initially, the light is very bright, but it slowly dims due to the capacitor gaining energy. Disconnecting works the same. It immediately is bright at the beginning of disconnection, but then it slowly goes back to being 0. And then we have the times needed for charging a 10 ohm RC circuit, discharging a 10 ohm RC circuit, and then the respective 20 ohm RC circuits. So we can see through this relationship expressed in the first two equations that a plot of Ln of the potential difference over the initial potential difference versus the time should yield a straight line with a slope of -1 over RC, where RC is the time constant. I plotted this data in the graph to the right. From this, we can get the slope is -0.642, and the estimated time constant is 6.09 seconds. Now, the actual time constant we can get from multiplying the resistance times the capacitance, so 0.2 times 30, which is 6 seconds, which is about the same as we calculated from the slope. The slight differences probably come from human error while timing the change in capacitor potential difference over time. But since the lab is entirely online, there shouldn't be any other sources of error. So if we were doing this lab in real life, how would using an actual ammeter affected our results? Well, a real ammeter has resistance, which we assumed that it didn't for this simulation. This would have meant that the equivalent resistance would be higher and that the current would have been lower. This would have also had the effect of increasing the time constant of the circuit, which would have led to higher times needed to charge or discharge the capacitor. If we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, the predicted time probably would not happen. This is because a circuit would have had both resistance in the battery and the wire, which we assumed that it wouldn't. As discussed previously, this means a greater time constant and also greater time needed to reach full charge. These are some of our conclusions.